Good day everyone, this is Edsel J. Lastimoso and I'm here to discuss about different complex waveforms, general equations of a complex wave, RMS value of a complex wave, and power supplied by a complex wave.
My heart is in Havana, He took me back to.
There are four different waveforms, namely the sine wave, square wave, triangle wave, and the sawtooth wave. Triangle wave is a non-sinusoidal waveform named for its triangular shape. Like the square wave, the triangle wave contains only odd harmonics. However, the higher harmonics roll off much faster than in a square wave. The term harmonics means a component frequency of a complex wave that is an integral multiple of the fundamental frequency. Sine wave or sinusoid, a mathematical curve that describes a smooth periodic oscillation. We can define oscillation as a flow of electricity changing periodically from a maximum to a minimum, or simply said, a flow periodically changing direction. Its most basic form as a function of time t is a sine times the quantity of 2 pi ft plus gamma, or equal to a sine times the quantity of omega t plus gamma, where a is the amplitude or the peak deviation of the function from zero, f is the ordinary frequency or the number of oscillations that occur each second of time, omega, which is equal to 2 pi f, as the angular frequency or the rate change of the function argument in units of radians per second, gamma as the phase, where in each cycle the oscillation is at t equals 0. When gamma is non-zero, the entire waveform appears to be shifted in time by the amount gamma over omega seconds. A negative value represents a delay, and a positive value represents an advance. The sawtooth or saw wave is a kind of non-sinusoidal waveform. It is so named based on its resemblance to the teeth of a plain-toothed saw with a zero rake angle. The saw wave contains both even and odd harmonics of the fundamental frequency. The convention is that a saw wave ramps upward and then sharply drops. However, in a reverse saw wave, the wave ramps downward and then sharply rises. It can also be considered the extreme case of an asymmetric triangle wave. A square wave is a non-sinusoidal periodic waveform, in which the amplitude alternates at a steady frequency between fixed, minimum, and maximum values, with the same duration at minimum and maximum. Although not realizable in physical systems, the transition between minimum and maximum is instantaneous for an ideal square wave. The square wave is a special case of pulse wave which allows arbitrary durations at minimum and maximum. The ratio of the high period to the total period of a pulse wave is called duty cycle. General equation of a complex wave. Consider a complex wave which is built up of the fundamental and a few harmonics, each of which has its own peak value of phase angle. The fundamental may be represented as voltage E sub 1 equals E sub 1m sine quantity omega t plus psi sub 1. The second harmonic E sub 2 equals E sub 2m sine quantity 2 omega t plus psi sub 2, and so on. Denote the maximum values or the amplitudes of the fundamental, second harmonic, and end harmonic. Psi sub 1, psi sub 2, and psi sub 3 represent the phase differences with respect to the complex wave or the angle between the zero of the complex wave and the corresponding zero value of the harmonic. The number of terms in series depends on the shape of the complex wave. In relatively simple waves, the number of terms in series would be less, in others would be more. RMS value of a complex wave. Let the equation of the given complex current wave be current I equals I sub 1m sine quantity omega t plus theta sub 1 plus I sub 2m sine times the quantity 2 omega t plus theta sub 2 and so on. Its RMS value is given by I equals square root of average value of I squared over whole cycle. Now, I squared equals the quantity of I sub 1m sine quantity omega t plus theta sub 1 plus I sub 2m sine quantity 2 omega t plus theta sub 2 and so on squared. The right-hand side of the above equation consists of two types of terms: harmonic self-products or the general expression, and the products of different harmonics of the general form. The average value of I squared is the sum of the average values of these individual terms in the above equation. We can generalize that average value of I sub 1m squared sine squared times the quantity of omega t plus theta sub 1 equals I sub 1m squared over 2, and average value of I sub 2m squared sine squared times the quantity of 2 omega t plus theta sub 2 equals I sub 2m squared over 2, and so on for the general term. Now, the average value of the product term is I squared equals I sub 1m squared over 2 plus I sub 2m squared over 2 and so on. Therefore, the RMS value current I equals the square root of I sub 1m squared over 2 plus I sub 2m squared over 2 and so on, which is equal to 0.07 times the square root of I sub 1m squared plus I sub 2m squared and so on, where I sub 1 is the RMS value of fundamental, I sub 2 is the RMS value of second harmonic, and I sub n is the RMS value of the nth harmonic. Similarly, the RMS value of a complex voltage wave is voltage E equals 0.707 square root of E sub 1m squared plus E sub 2m squared and so on. Power supplied by a complex wave. Let the complex voltage be represented by the equation voltage E equals E sub 1m sine omega t plus E sub 2m sine 2 omega t and so on be applied to a circuit. Let the equation of the resultant current wave be current I equals I sub 1m sine quantity omega t plus theta sub 1 plus I sub 2m sine quantity 2 omega t plus theta sub 2 and so on. For obtaining the value of this product, we will have to multiply every term of the voltage wave in turn by every term in the current wave. The average power supplied during a cycle would be equal to the sum of the average values over one cycle of each individual product term. However, the average value of all product terms involving harmonics of different frequencies will be 0 over one cycle, so that we need to consider only the products of the current and voltage harmonics of the same frequency. Power supplied by a complex wave. Let the complex voltage be represented by the equation voltage E equals E sub 1m sine omega t plus E sub 2m sine 2 omega t and so on be applied to a circuit. Let the equation of the resultant current wave be current I equals I sub 1m sine quantity omega t plus theta sub 1 plus I sub 2m sine quantity 2 omega t plus theta sub 2, and so on. For obtaining the value of this product, we will have to multiply every term of the voltage wave in turn by every term in the current wave. The average power supplied during a cycle would be equal to the sum of the average values over one cycle of each individual product term. However, the average value of all product terms involving harmonics of different frequencies will be 0 over one cycle, so that we need to consider only the products of the current and voltage harmonics of the same frequency. So the average value of power equals voltage E sub Nm times current I sub Nm times cos theta over 2, or equal to voltage E sub N times current I sub N times cos theta sub N. Therefore, the total power is P equals voltage E sub 1 times current I sub 1 times cos theta sub 1 plus voltage E sub 2 times current I sub 2 times cos theta sub 2, and so on, where voltage E sub n and current I sub n are the RMS values of the voltage and current respectively. Hence, total average power supplied by a complex wave is the sum of the average power supplied by each harmonic component acting independently. And the overall power factor is given by PF equals total watts over total volt amperes, where E, mainly the voltage, equals the RMS value of the complex voltage wave, and I, current, equals the RMS value of the complex current wave. Hello everyone, so we have a problem here we're gonna solve. A complex voltage is given by voltage E equals 60 sine omega t plus 24 sine times the quantity 3 omega t plus pi over 6 plus 12 sine times the quantity 5 omega t plus pi over 3 is applied across a certain circuit, and the resulting current is given by I equals 0.6 sine times the quantity omega t minus 2 pi over 10 plus 0.12 sine times the quantity omega t minus 2 pi over 24 plus 0.1 sine times the quantity 5 pi minus 3 pi over 4. So we have to find the A, RMS value of the current and voltage, B, total power supplied, and C, the overall power factor. So first, we have to list down all the given from voltage and current here. After, so in such problems where harmonics are involved, it is best to deal with harmonics separately. So by the way, this is an odd harmonic, so first, third, fifth, seventh, and so on. Okay, so we then proceed to the formula of getting the power, which is voltage E sub 1m times current I sub 1m over 2 times cosine theta sub 1. Now, you can see multiplying voltage times current, so 60 times 0.6 over 2 times cosine 36. So cosine 36 is obtained after evaluating 2 pi over 10. So solving for the problem, 60 times 0.6 over 2 cosine 36. Now obtain 14.56 at first harmonic. So here, then next on the third one, same procedure, multiply voltage to the current over 2 cosine 45. Here, after evaluating pi over 6 and 2 pi over 24, add both of them, we get 45. So solving for this one, we then now get, okay, 8, 1.02 watts. You can see, okay, 1.0 watts at third harmonic. The next, same procedure with the first and third. Okay, multiply 12 to 0.1 over 2 cosine 75. Okay, evaluate this and this again, then add both of them, you get 75. Then 12 times 0.1 over 2 cosine 75. We then now get the value of 0.16 at fifth harmonic. Now we have them. We then proceed to get the RMS value of current and voltage. So in getting the RMS current, we have the formula of the square root of all the currents over 2 squared. Okay, yeah. Then substituting the currents, okay, we have first current, second current, and the third current is 0.1. Okay. Calculating, we then obtain 0.438 amperes. Proceeding to the RMS value of the voltage, here, same procedure, square root of the voltage squared over 2, sum of them, the sum of all. Then here, voltage 1 60, voltage 2 24, and voltage 3 12. We obtain 46.5 volts. So proceed to letter B, which is the total power supplied, which is a lot easier to solve. We just have to add all the wattage we've got earlier, which is here 15.56 watts, 1.02 watts, and 0.16 watts. So adding the 3, we then obtain the total power of 15.74 watts. So after all, we now proceed to letter C, which is the overall power factor. So the overall power factor is equal to the total watts over the total volt amperes. So we obtained earlier the total power, which is 15.74 watts, okay, times the total volt amperes, which we have to multiply 0.438 amperes to 46.5 volts. So here, calculating, 46.5 times 0.438. We now attain the value of 0.773. So the overall power factor of the circuit cannot be stated lagging or leading. It is simply because the ratio of power in watts of volt amperes. Yes, that's all. Thank you.